Okay, so let's say you have mass and spring, multiple springs and dampers in series or parallel, but we want to not deal with a ton of algebra. I am not a huge fan of tons of algebra, so I love working through this way. It is a bit more abstract because what we're going to do is we're going to set up our system entirely from free body diagram to finish. I guess not from start to finish, but from free body diagram to finish in the Laplace domain. Because if we do that, then we can treat springs in series as resistors in parallel, where the equivalent spring will be equal to the summation of the inverses of every element. So let's say that we have that same system from before in the previous video, or if you're just watching this, this should be the one that we did in class with our notes. So we have two springs and a damper attached to the floor, and we have a spring and damper in series attached from our input to our output. And we also have a mass in between. So I'm going to tell you springs in series can be treated as resistors in parallel and vice versa. So if we have springs in parallel, those can be treated as resistors in series. So we're going to draw the free body diagram, and we're going to say that there's some equivalent spring multiplied by x of s and some equivalent spring multiplied by x of s minus y of s. So I drew the spring in tension. X will increase the tension, y will decrease the tension. I could have drawn that arrow the opposite way and just said k e2 y minus x. So that's just what orientation did you use. That's separate to how we treat our springs in series or parallel. If you're still having trouble with that, I'd recommend looking at the PDF posted on Canvas. But anyways, we can say that there's an equivalent spring at the bottom and an equivalent spring at the top. And the equivalent spring at the bottom, its springs in parallel can be treated as resistors in series, which means we're just going to add them up. So our equivalent spring can be seen as k plus cs, and then for ke2, we could say the inverse of ke2 is equal to the inverse of our spring element plus the inverse of our damper element, which means that our equivalent spring would be equal to kcs divided by k plus cs. Some of our masses, we have that both of these equations are pointing up, where our x is pointing down. So ms squared x of s is equal to negative 2k plus csx. So that's just that k equivalent 1 times x of s, but it's pointing up where our direction's pointing down, so we have a negative term. Minus k of kcs over k plus cs, so that's our k equivalent to x minus y. And that's almost it for algebra. We then can go ahead and isolate our x terms and our y terms, but it's a lot less to deal with than a dummy variable. And I have this all written out for you in the PDF listed below. So that's how we could do it in the Laplace domain. It's a lot more simpler in terms of the math and algebra, and it's a lot more abstract in terms of what's going on since we're working entirely in the Laplace domain. One reason I don't talk about this in class is I see a lot of students who learn this method, then they struggle when they get to electrical systems because of how we deal with certain electrical elements. So if you're not strong with this stuff, I would say stick with the dummy variable. If you do like having shortcuts and you're comfortable juggling them, this is a great way to work through. Okay.